28, we're up to the third class. There are some people adding. Hopefully they will find this. You can view the videos from old classes. Everything is at samsclass.info. You go to 128, and here's the videos of the previous classes and the homework and such. And we're down to the second part of analyzing Android applications. And then I'll just demonstrate another project, M107 and 111. So let's take a look at the slides, which are here. Okay. So, make them big. All right, good. Looks like things are working. So, we did this part before, getting your Android environment working. Now we're going to talk about the security model and more about that next time. So here's the, this was all in, anyway, this is what we're going to do. Code signing, understanding permissions, the sandbox, and file system encryption. So the security model of Android is very strange. I mentioned it before. It is very different than the security model of, say, Windows executable software. Windows executable software is expected to be signed by a developer with a real certificate purchased from a certificate authority that can be verified. And Windows will typically refuse to run anything that's not signed and warn you and all that. Android doesn't have any of that, because the whole point of Android is it's supposed to be open source, and you are supposed to be able to write code and distribute it without getting anybody's permission. So you can just email it to people, put it on your own website, submit it to the Google Play Store, and they will put it in there with only a rudimentary check to see if it's malicious. And if it is malicious, they'll take it out. And if they kick you out, you can just make another account under a fake name and put up the stuff again. So it's an open ecosystem like Linux without a lot of controls. That's the idea. Now, all right, Android does need to know whether the app was made by Google or not, because Google apps get special permissions. But other than that, everybody else is just a self-signed certificate with an arbitrary name. So code signing, I've talked about. This is a real important security feature. And the way it works is you have a digital certificate. You get it from a certificate authority, and it used to be expensive, although now you can get them free from Let's Encrypt. And this creates a new public key and assigns it to you. And then you get a certificate, and you can send that certificate to people, and it will have the correct public key to use to send you messages. The private key is on your system and kept private, so you can read them, but nobody else can, and it's all verified with a third party. But in this case, we're going to use self-signed certificates. So they are not signed by a certificate authority, and they cannot be verified anywhere. The cryptography is the same, but there is no actual authentication to prove that you are who you say you are. So I could make a certificate and claim to be Google, claim to be Microsoft, claim to be Facebook, and there's nothing in the system to prevent that. However, your Android operating system will not be fooled because it knows where the real Google is. But I could have a company named Google, and it would look the same to the user, but it wouldn't look the same to the operating system. So you get it, you can unpack an app. You'll do this in the projects. You download the Progressive app, and then you unpack it with APK Tool. APK Tool D will take apart an app, decompile or whatever you call it, open it up. The app is just a zip file containing a lot of features, and it's the text files are not exactly in the readable form, so it has to do a little more than that. But this will decompose the APK file. And then you can go into the meta.inf folder, and you can see the certificate. And the certificate itself is a file that you can't print in plain text, but you can use KeyTool to print the certificate, and here you'll see the owner is Matt Lehman, Progressive Insurance, and so on. It has a certificate fingerprint. So this thing is signed by somebody that claims to be Progressive, and as I said, the weakness is it doesn't have any way to verify that it's really Progressive. You could just be anybody claiming to be Progressive, and nothing in the Android ecosystem would make it possible to tell that that is not true. So if you use OpenSSL, you can see another view of the certificate here, and you can see the public key, which, remember, this is the point. This 1024-bit public key is the active ingredient in a certificate. That's a public key you can use to encrypt data, which can only be decrypted by the holder of the certificate. And I think I see some comments in the Twitch. Nope, okay, good. All right, and so if you go down here, you'll see the signature algorithm. There's a signature, which is the main thing you care about, and then a base64 version of the certificate. And so in addition to enabling encryption, the certificate also enables you to sign the app, and the purpose of that is you hash the app then you sign it with your private key. Anybody can verify it with your public key, and so they can verify that the app has been signed by the person who gave you that public key, and it has not been modified after the signature. That's what it verifies. But since you can just recreate a new signature and re-sign it again, which is what we're going to do, this provides very little guarantees. The only sense in which it provides any good guarantee is if you install an app from, say, a trusted source like the Play Store, and then I try to send you an update for that app that is not signed with the same private key, Android will refuse to accept it. So that is the one bit of security you get from this. You know that updates of your app are coming from the same person who sent you the original app. I could trick you into installing a fake app right from the start, and then it wouldn't detect that or tell you. Now, some people use MD5 as a signature, and in fact, that's perfectly fine. MD5 does have collisions, but the fact that you can maliciously, carefully create two files with the same MD5 is not the same as creating a fake certificate with somebody else's MD5. That is still out of reach. And there's a website that explains the mathematics of this. Just finding a collision is pretty easy because you carefully craft two files that are related in a way that they'll have a collision. But if somebody else has signed something with a certain MD5 or SHA-1, and you're trying to find another private key that will create signatures with that same MD5, that would take forever. Even though there are collisions, they're not that easy to find. But in fact, most people use SHA-256 these days, so I think Android still uses SHA-1 or MD5. So it doesn't verify the certificate in any way. They're self-signed, and so it's only checked when an app is installed. They recommend that you make your certificate valid for 25 years or longer, because you'll have to keep using that same certificate for all the updates. And when that expired, it would refuse to take updates. So you'd have to tell all your customers to uninstall it and reinstall it. That's why you just make it a long time, the entire projected lifetime of your app. All right, so there have been some signing vulnerabilities. In addition to the fundamental flaw of not validating the certificates, there have been actual bugs in the certificate validation process. Here's a few of them. The master key was one from 2013. If you remember, the APK file is just a zip archive containing many files. Well, you can create two files in there with the same file names. And if you do that, only the first file's hash is checked, but the second one is actually deployed to the device. So you can trick it into passing the certificate, the signature check, and then deploying a different file. And this, I was amazed when I first read about defeating Microsoft signed code. I said, how could you possibly do that? And it turns out that Microsoft has similar vulnerabilities. It doesn't actually sign every segment of the code. So you can sneak in altered code in the segments that aren't signed. This is true of almost every defense. It sounds good until you look how it's actually implemented, and it turns out there are holes, places where the defense is not actually used. Another one like that is address space layout randomization, which randomizes the location of code in a Windows system. When we do the exploit development class, which I guess will probably be next semester or the semester after, you'll see you can still exploit machines because some code is not randomized. It's always in a predicted location, and so that becomes the weak spot. Anyway, then there was an extra field length. You could add an extra field here, but Java treated it as a signed integer. And therefore, it's 16 bits, you can overflow it, and it would become negative. And then the length of this would be negative, so then you could inject arbitrarily long amounts of extra field, and that was another way you'd be able to inject things. This is another one of the very common vulnerabilities, is an integer overflow, where a length can be turned negative, and then you won't pass. It tries to check to make sure your length is not above a certain value, and that will fail if the length is misunderstood as a negative number. And then name field length was another one. It doesn't check the length at all by the Java verification code, so you could inject code into the file name. So these are various flaws that have been present in the way it handles certificates in Android. I think all these have been patched long ago, but if you have an old version of Android, it'd be vulnerable for them. Now, here's the permission model. Remember, we talked about this before. When you install something, it will tell you this has access to the camera and your contacts and your Wi-Fi and so on, and then you can accept it here. That goes into the manifest file, so you'll see it has read phone state, access network state, internet, access Wi-Fi state, and so on. These are the permissions that are approved for this app. Now, it turns out there are some gotchas here too. You can define a new permission. Notice there's standard permissions like Wi-Fi, but you might want to define a new permission. If you do, like I can define some permission, a Skype permission called C2D message, something about having to send a Skype message. So if I define that permission, then I can define a protection level. And the protection level here is set to signature. So if you define a new permission just for your app, then here's the option. Normal is the default value. Dangerous is a higher risk permission. Signature is the one recommended. This means that the only apps that are allowed to have this permission are ones that are signed with the same certificate. So that would be only the apps from your company are allowed to have this permission. That would seem like a pretty good idea, so no other apps can have it. And then you can have signature or system. System apps are the ones from Google I mentioned before. Your phone recognizes Google apps and gives them special privileges. So those are options. Now the normal one lets you have access to application features at minimal risk to others. This is the default. And dangerous, the system may not automatically grant it to the requesting application. It may be displayed to the user and require confirmation before proceeding or something like that because it's considered dangerous. All right, that's point. System is part of the Android system image, and development or other permissions applied at runtime, not commonly used and poorly documented. This is true of all operating systems, including Windows. There are features that are undocumented that people discover and sort of guess about. Things that are not intended to be used by normal developers. So signature protection is recommended, of course, unless you really need to share data with other apps. That would make sense. Then you're only going to share data with the apps your company wrote, and that would be safer. So malicious apps that want to install extra permissions, they can just ask for permissions and hope the user will allow it, which usually they will. The user will usually just not even read or understand that box and just click OK to install it. The same thing's true of most error messages, like SSL error messages and all the others. Now, more than 90% of users just close every error box and keep going, don't know what it means, don't care. Or you can find a kernel exploit, like Gingerbreak or others. If you have a kernel exploit to escalate to root, then you can install permissions without notifying the user. All right, and then we can talk about the sandbox. Let me just check for questions in the Twitch. Dangerous means the human must confirm with each use. Yes, or something like that, Akaran, yes. It will apply some attempt to warn the user that this app is doing something dangerous and suspicious, which would be not probably of some use. All right, so the sandbox is extremely simple. I remember I heard the sandbox and I imagined that every app was running on a virtual machine, and that is not true at all. All it is every app is running as a different user account. So Coinbase runs as U0A145 and Schwab runs as A129, each just like two users logged into the same machine. So, all right. And it can request to run with a shared signature as another app if you have two apps from the same company that want to do that. And some allow world execute. You notice here the Schwab app can be run by anybody, XXX. These are the permissions, but most of them are this way. They can only be run by that account. So that's the sandbox. It's not a separate virtual machine. It's just a separate user account for each app, and then it uses standard Linux users accounts. So the other users don't have right to read the data from another app. All right, and then file system encryption. This is a sore point. If you have an iPhone, you are amazingly safe. You can take an iPhone, if it's model 3S or later, which I think every iPhone in use probably is by now, if you go into settings and restore it to factory defaults, you can sell that iPhone or give it away, and none of your data will be exposed. And this has been confirmed. There was a forensic company that bought 100 used iPhones off eBay and tried to read the data, and they couldn't recover any usable data from any of them. So it really works. Now, the reason it works is as soon as the iPhone, before you ever use your iPhone, encryption is turned on. Everything you ever do on it, from the first time you touch it, is all encrypted with AES. And the key is stored in a particular location, and the restore to factory default simply deletes the key. So the data is still there, but it's encrypted with a key you don't have, and that is effectively perfect. And it also means it's very fast. It doesn't have to go out and write over all those blocks to scrub them or anything. It just deletes the encryption key, bam, and all that data is gone. This is a great thing, and it would be great if Android did it. But Android doesn't do it because, again, it's a free open ecosystem. Android is open source software. Anybody could make a phone and use Android. You don't have to follow Google security recommendations. If you deviate too much from Google security recommendations, they will block you from having the Play Store on there. But there are phones that don't have Google Play, and they're just cheap, and they have all kinds of security flaws. So in principle, full disk encryption has been available since Android 3, but many phones choose not to enable it to save power. Android has a huge problem with battery life. You probably noticed I had an Android phone, and the battery wouldn't last all day. And if iPhone, it does. And this is because iPhone apps have to conserve power. Apple is strict about that. When you propose an app and try to put it in the Apple Store, they test the app to make sure it's not wasting power. When I tried testing apps on Android, there were apps that were just running at 100% CPU all the time because the developer was an idiot and so on. There's no enforcement. And I went to Google I/O conference, and I attended the talk where they explained how to conserve power in your app. And there were these lengthy, difficult tools you're supposed to run, which nobody knows about. Most developers don't know, and they don't enforce it in any way. So Android apps tend to waste power, and it's a problem. So one way they conserve power is by not encrypting the hard drive. So that's a disturbing. But the later version, but if you have a relatively modern phone, especially if you have a high-end phone like a Google Nexus, it's probably encrypted all the storage just like an iPhone. But your cheaper phones won't. And here's another really big fundamental security problem with Android, which is that many people are using very old versions of Android. Most carriers block the updates. If you have a carrier, they will typically charge extra money for features like, say, tethering to your phone, and then Google will offer an update that adds that feature for free, so they block the update. So typically, you can't get the updates on your phone, and people don't, and they use old phones. So you see the versions are scattered all over the place. There's Android 10 down to Android 4, and even 2.2 is blue. And you see even in 2020, they're just all over the place. The number of Android phones that are running the latest version is a small number all the time, whereas iPhones, it's like 90%. So this is a huge problem, and the fundamental root cause of all this. Even really old attacks will work if you have an old phone, and a lot of people do, of course. So that's probably the single biggest problem with Android, is people using out-of-date phones that don't have the patches, and there is no patch available from their carrier. So there's really no way for an ordinary user to fix it. And this is why some people prefer to replace the Android with a custom ROM under their own control, like Clockwork ROM or something, and then you can update it yourself. That's an option. You can hack your phone and put on your own operating system and put on your own updates, and then it's under your control, but that's only for like the 1% most technical users. Most users buy the phone and use it the way it is, and don't really notice or understand that the fact that it's been a couple of years and there haven't been any updates is a bad thing. All right, so here's other encryptions. The SD card, which is removable on some phones, is not encrypted. And encryption only protects data at rest. So if you install a malicious app and the app attacks your data in use, encryption does nothing. Now, in principle, if the sandbox is working, the app will not have permission to read other apps' data, but if it finds a vulnerability on your phone, for example, because your phone is a version or two out of date, then it'd be able to escalate to root and steal the data from the other apps on the phone. All right, let me check for questions here. Yeah, that's right. Good. Okay, no questions. Let's try this Kahoot, which is here, 128.6b. There. All right. got everybody that's coming. All right, so what does an app signature prove? Yeah, none of them. It did not come from a certificate authority. It doesn't prove that it came from Google Play, and it doesn't tell you who the developer is. It proves none of those. That's why it is pretty amazing. They're using the X509 certificate in a way that actually undoes most of the security guarantees that X509 certificates generally provide. All right, what vulnerability used two files with the same file name in an APK file? That's the master key vulnerability. By the way, there's a similar web vulnerability called parameter pollution, where you define a parameter twice. And if you're lucky, the first value is used for the if statement for verification, but the second value actually goes in. So you can sneak things in you're not allowed to do there. Same kind of thing. The same thing also happens with authentication of the type used by Canvas. Security assertion markup, like SAML packets, often let you put extra data in which is not validated but still believed by the server. That was a common flaw in SAML software up to a few years ago. It's mostly been patched now if you're using the latest version. So which file lists the permissions an app requires? Manifest. All right. And what permission level should an app use for new permission? Signature is recommended. If you don't really have to share this permission with other companies' apps, why do that? Restrict it to only your company's apps, and then whatever messages are being sent there, you know they're only going to your company's apps. And that looks like a real name. And CF12, I think we know who that is from before. Again, it looks like a real name, so I think good. You folks should get your points. All right, let me stop this recording.